Okay, we'll now do November 21, P13. This is the last paper variant that we have. Okay, so we try to cover as much as we can. Okay, now question 1. You have a paperback book that contains 210 sheets of paper. Its thickness is measured with a ruler as shown. What is the average thickness of one sheet of paper in the book? Okay, this one is something like just testing your ability to measure something using a ruler. So your length, you can actually see from here that this one is 3.6 centimeter. This one is 0.9 centimeter. So the difference between those two is going to be your length. 3.6 minus 0.9 giving you 2.7 centimeter. So this one here is 210 pages. They want you to find the thickness of one page or one sheet. So thickness is the length divided by number of pages is 2.7 divided by 210. You're going to get 0.0129 centimeter. But they want the answers in millimeter. Okay, so you have to do something like some conversions here. So in my case, because I had it in centimeter, I want to convert it back to centimeter, from centimeter to meter. It will be that same value multiplied by 10, multiplied with 10 power minus 2. But at the same time, I want to convert it to millimeter, right? So I divide by 10 power minus 3 to convert it to millimeter. So the final answer is 0.129 millimeter. Okay, so round to 2SF is this, is answer C. Okay, so maybe I better just mention this. This one is from centimeter to meter. This one is from meter to millimeter. Okay. Now, number 2. What is the unit of resistance when expressed in SI base units? Okay, so this one, yeah, we know that the unit of resistance is ohm. This is actually the special SI unit, but the question wants base units, so we cannot say that it's just ohm. We need to express it in terms of SI base units. So one of the easiest equations to start off with would be probably to use P equals to I squared R. Power is work over time, rate of work done. Then I is ampere. Okay, so power is rate of work done, so it's W over T, then equals to I squared R. R is Fs over I squared T. The work here, I change it to Fs, force times distance. So I'm getting this expression here. Now with this, I can actually find out the unit of R in terms of SI base unit. The unit of force times distance or displacement is kg meter per second square multiplied with meter. The unit of current is ampere square times with time unit in second. So the final answer becomes kg meter square second power minus 3 ampere negative 2. Answer is D. Okay, so this one is pretty straightforward. I don't really need to change the equation for current. The unit for current is in ampere. That one is already in SI base units. So I don't really need to bother changing current. All right, I can just leave it as it is. The only thing I needed to change was the power portion so that I can get it in SI base units. All right. Okay, so this one is okay. Now, number 3, which list consists of only scalar quantities? So some other things you can just see from here is this. Acceleration is vector, displacement is vector, force is vector, weight is vector, density is scalar, energy is scalar, frequency is scalar, velocity is vector. Then D, momentum is vector, power is scalar, volume is scalar, wavelength is scalar. So none of these are what we want. We want only scalars. So if you look at answer choice C, distance is scalar, pressure is scalar, temperature is scalar, time is also scalar. So these are all scalars. Answer is C. Okay, so there's no big issues here. Then if you continue on to question 4, the output of a signal generator is connected to a CRO. The trace is now shown on the screen. The time base of the CRO is set at 2 milliseconds per centimeter. What is the frequency of the signal? Time base here refers to the horizontal scale. Okay, they're telling you 1 centimeter is now 2 milliseconds. Okay, so what is the frequency of the signal? The easiest thing to do for you is to find out the period. This is the period. So period is actually 4 centimeter multiplied with 2 milliseconds per centimeter. You're going to get the period as 8 milliseconds. So frequency is the reciprocal of the period. 1 over 8 times 10 power minus 3. You're going to get the answer is 125 hertz. Okay. You're getting the answer for period in milliseconds. So you have to multiply with 10 power minus 3 to change it to seconds. Okay. So just bear that in mind. All right, then after that, we look at question 5. Okay, this one requires a bit of imagining, right? They tell you after measuring the width of a shelf to be 305 millimeter, it is found that the graduations on the ruler used are 1% apart than they should be. Graduations on the ruler refers to the divisions on the ruler. When you look at your ruler, you notice the line divisions, right? That is your graduations, okay? Graduations here refer to the line divisions on your ruler, okay? They found out that the line divisions on your ruler is actually 1% further apart than it should be. So what type of measurement error is this, and what is the true width of the shelf? Okay, so we know that this one by right should be systematic. Okay, right, but how much is the actual width of the shell? Now, with your graduations further apart, before I go and explain the answer further, with your graduations further apart, the line divisions further apart, any measured value is actually supposed to be less than your true value. Therefore, it's actually your systematic error. If you use this same ruler with the graduations further apart, your measured value will always be less than your true value. So remember, I mentioned that systematic error is where all your measurements are always either above or below your true value. If one of them is above, all of them should be above. If one of them is below, all of them should be below. That is what systematic error is. So with your case here, since your graduations are further apart, if you use that same ruler to do any measurements, your measured value will always be less than your true value. So it's actually systematic error. Now you may be wondering, how do I know that with the line divisions further apart, how do I know that the measured value will be less than your true value? You just think of it as this. It will be easier to imagine it from the diagram below. You imagine this is the object that I want to measure. Okay. If the graduations or the line divisions on the ruler was accurate, like the one seen here, this one will give me exactly 0.5. But what the question mentioned was that your graduations or line divisions are 1% further apart, meaning to say they're actually 1% further. So the ruler that you're currently using has graduations that looks like this right now, where the line divisions are further apart. Now, if you use this same ruler to measure your object, that same object, notice that your ruler reading will now be somewhere around here. Okay, so if this one was 0, 0 0.1, 0 0.2, this one is 0 0.3, and then this one is 0 0.4. So maybe for the sake of discussion, I say that this is 0 0.32. You see, it's actually less than the true value. So if you use this same ruler to measure anything else, you're always gonna end up getting the value lesser than the actual one. Okay, that's why I can say this. with your graduations further apart, your measure value will always be less than your true value. So it's systematic error. Okay, that's how I got this part. Now, the next part will be finding out the true value. Okay, so you can basically, so the thing now is that you want to find the true value. If you know what's the error, can you then work out what is the actual value? So this one is point number 2. Since the graduations are one further apart, your measure value is actually less than true value by 1%. Just now here we already determined your measure value will always be less than the true value. So since your graduations or line divisions are 1% further apart, your measure value will be less by 1%. Okay, so this in turn means this now. Your true value is supposed to be 1% higher than the measure value. Think of it another way lah. Okay, if measure value is less than true value by 1%, that means true value is 1% higher than measure value. So true value is 1.01 times 305, giving you 308. Answer is D. Okay, right? Yeah, this one will take some time to wrap your head around it, so you try to digest it slowly. This is the type of question that people normally won't be able to finish within 2 minutes. Okay, so this one requires some thinking. Okay, so take your time to digest this. Okay, but this is the workings. All right, answer is D. This 305 here was your measured value. Okay, they already told you here. Okay, so this one is fine. Then I move on to the next question. All right. Okay, so next question, number 6. Now, number 6, the graph shows you the variation with time of the acceleration of a car. What must be the shaded area under the graph? What does it represent? So since we know acceleration is the rate of change of velocity, where A is delta V over delta T, delta V is area times delta T. Okay, so you see, if we have a graph of acceleration versus time, the area under the graph is actually A times T. So what does A times T represent? We have to look at the definition of acceleration. So acceleration is rate of change of velocity. Change of velocity is actually acceleration times the change in time. So it's actually representing to us change in velocity. Okay, so answer is B for number 6. Okay, all right, then after that you have number 7. Number 7 is on kinematics already. A stone is thrown horizontally off a cliff and it lands in the sea. Air resistance is negligible. Which statement about the stone's motion is not correct? Okay, so what is not correct about this situation? So that would mean that since you're trying to find out which statement is not correct here, the answer is D. The rest of the 3 statements are actually correct. It's only D that is wrong. Okay, so let's just briefly read through the answer, then after that I explain to you. The explanation is under page 20 of the work solutions. A, they tell you the final displacement of the stone depends upon its initial horizontal velocity. This one is correct. The stone travels with constant horizontal component of velocity until it hits the water. This is also correct. The stone travels with an increasing vertical component of velocity. This is also correct. The one that's wrong was that time taken for stone to hit the surface of the water depends on its initial horizontal velocity. This is wrong. Okay, so why is this wrong? Wait, I just know what page was this. I will go back and forth from here and there. This one was page 6. Okay, let's go to page 20. Now, it will probably be better to visualize this. So, the question mentioned that you have a stone that is thrown horizontally. Okay. The question specifically mentioned to you that you throw the stone horizontally off a cliff so that it lands in the sea. Air resistance was negligible. So because air resistance was negligible, there are actually two things to note from that. This one is one of the first thing that we learn under kinematics. Okay. The first one was that since air resistance is negligible, you should have constant horizontal velocity. Horizontal velocity would remain constant until the stone hits the sea. Okay, so this one here would have made answer choice B correct. Okay, B would be correct. You would travel with constant horizontal velocity because air resistance is negligible. This is actually the important thing to note here. Okay, right? Then after that, what about the rest of the answer? The other thing that we mentioned here was that it's also because you have constant horizontal velocity. You look at the horizontal velocity portion, a higher initial horizontal velocity causes the stone to travel further horizontally. Okay, so what I mean by that is this. You see, if, for example, to give you an extreme case, if your first case was that you threw the stone with 1 meter per second, and then we tell you that, okay, let's just say, for example, I give you some random value. Time to fall is equal to, say, 5 seconds. Okay, right? So if your object was moving with an initial horizontal velocity of 5 meters per second, your distance traveled would just be 5 times 1 equals to 5 meters. So you only end up at 5 meters over here. But what if I told you that rather than using 1 meter per second, your object was thrown at 10 meters per second? So now your new displacement horizontally will be 10, it will be 5 times 10, giving you 50 meters. So you will end up over here now. So this one will be 50 meters. Okay. So initial horizontal velocity, a higher value will cause your stone to travel further horizontally. So your final displacement actually depends on your initial horizontal velocity. Okay. Because you see here, under page 6, it was mentioned that the final displacement of the stone depends on its initial horizontal velocity. This is true. If you if the stone was projected with a higher speed, you obviously travel further. So it will affect your final displacement. Okay, so A was also correct. Okay. Now, then another thing here was this. The time taken to hit the sea, the last thing to know about the horizontal portion was that the time taken to hit the sea depends on your vertical distance traveled and vertical acceleration experience, not on your initial horizontal velocity. Okay, what do we mean by that is this. You see, if say for example, I told you that this is, say, a distance of, for the sake of discussion, I told you is 100 meter. Okay, and this one, your uy was 0. You have a gravitational acceleration equals to g. If I ask you to find out the time taken to hit the ground vertically, this one is talking about the vertical motion. V is equals to u plus at. Downwards is considered to be my positive because downwards is my initial direction of motion. So I don't use V equals to u plus at. I use s equals to ut plus half at squared, sorry. Ut plus half at squared. Okay, so in my case, it will be 100, it will be 0 plus half 9.81 t squared. So that t is 100 times 2 divided by 9.81, square root of that is going to be 4.5 seconds. Okay, so now you consider this now. If I told you just now I had an initial horizontal velocity of 1 meter per second, the initial vertical velocity will still be 0. The vertical distance will still be 0. The vertical distance will still be 100 meter, and my gravitational acceleration will still be g. The time taken to fall to the ground will be 4.5. But what if I change my horizontal velocity from 1 meter per second to 10 meter per second? Would it affect the time taken for your ball to fall to the ground? It actually won't affect anything. Because if you look at the vertical motion again, applying this equation, even at 10 meter per second for your horizontal velocity, your initial vertical velocity was still 0. Your vertical distance is still 100 meter. Your acceleration vertically is still g. So nothing changed. Your case here is still the same as before. You will still take the same time to fall to the ground, sorry, to fall to the sea vertically. Okay, remember I mentioned to you before that time taken to move horizontally to a point is the same as the time taken to move vertically to a point, which is also in turn the same as the time to fall. If it took you 4.5 seconds to fall vertically, if it took you 4.5 seconds to fall vertically to hit the sea, it will also take you 4.5 seconds horizontally for you to hit the sea. So overall, it will still be 4.5 seconds for you to go from here to here. That was what this one meant. Okay. So now looking back at this, the thing that I just want to illustrate is that your time taken to fall will still be the same, regardless of your horizontal acceleration. Okay, that's why here I say time taken to hit the sea depends on your vertical distance travel and vertical acceleration experience. It doesn't depend on your initial horizontal velocity. In my case, this vertical distance and vertical acceleration did not change. So my vertical, in my case, since the vertical distance and the acceleration did not change, you don't expect the time taken to fall to actually change. It will still remain the same. Okay, so what does this actually relate to? It actually relates to this part. The one you see here, D, time taken for the stone to hit the surface of the water depends on the initial horizontal velocity. This one is actually not correct. Your initial horizontal velocity does not affect anything. Okay, it doesn't affect your time taken to fall to the ground. Sorry, time taken to fall to the sea. It depends on your vertical distance and your vertical acceleration. Basically, it depends on this vertical distance and this vertical acceleration. This will be the one that actually affects the time taken. Okay, right? So that one is okay. So D was actually the wrong statement. Okay, now there's also one case I haven't considered for you yet, the part where we're talking about the vertical acceleration. When your air resistance is negligible, you have constant vertical acceleration. So your vertical velocity tends to increase at a constant rate. Okay, because you can see from here, if I top off everything, when you throw your object horizontally from the cliff, your initial vertical velocity is 0. But then over time, because you have an acceleration downwards like this equal to g, your vertical velocity will tend to increase. And it increases at a constant rate. Constant rate would mean something like this. Vy versus t is a straight line. Like this. This is what we mean increasing at constant rate. Because you see, if you try to divide it into equal intervals, this delta t, and this delta t, your change in velocity is the same. This one delta v, delta v, delta v. Okay, the velocity is increasing by the same amount each time. If I tell you that this one was 3 meters per second, this one will be 3 meters per second. This one will also be 3 meters per second. It's increasing by a constant amount. Basically, you can say something is increasing at a constant rate if you just see a straight line. Okay, that tells you that your values are increasing by a constant amount. Okay, what is this related to? Is related to C. Okay, the stone travels with an increasing vertical component of velocity. Okay, which is actually what I just explained to you. Your velocity ought to increase because you're speeding up as you're moving down. Okay, so you're speeding up as you're moving down because you have acceleration. Okay, now the increasing at constant rate one, just now I think I over-explained it. The question actually didn't really bother about what rate was it increasing, but I go and explain to you it was increasing at constant rate. Okay, how do I know it was increasing at a constant rate in the first place? It's because my acceleration is constant. You see, A is rate of change of velocity. The value of acceleration is the gradient of your VT graph. So if I try to plot to you the graph of acceleration versus time, it will be a straight horizontal line like this. And it will be positive because downwards is your sign convention. Okay, and your G is also downwards. So they are positive. So this one is constant, positive value. In return, your gradient should be constant, positive gradient. That's how I know it's like that. Okay. Right. The last few points was this: time taken for stone to hit the sea is longer if vertical distance between cliff and sea is larger. More distance, more time required, or vertical acceleration of stone is smaller. It's moving slower, so more time is required. This is actually related to what I just mentioned for this one, okay? Where I tell you that time taken to hit the sea depends on vertical distance traveled and vertical acceleration experienced, okay? So it doesn't depend on your horizontal velocity. All right. Okay, so the full explanation was in page 20 now. You can just take your time to copy it later from the work solution. But this is the work solution explain all this already. All right. So take your time to digest that. Okay, now for question 8, water is pumped through a hose pipe at a rate of 90 kg per minute. Water emerges horizontally from the hose pipe with a speed of 20 meters per second. What is the minimum force required for a person holding the hose pipe to prevent it from moving backwards? Okay, so how to find the minimum force? This one by right you should already know, or you're basically talking about rate of change of momentum. So what is happening here is this. They tell you water is pumped through a hose pipe at the rate of 90 kg per minute, and it emerges horizontally from the hose pipe at a speed of 20 meters per second. So your water emerged from the hose pipe at 20 meters per second. So the thing here is this, the water emerging from the hose pipe at 20 meters per second means that there is a force being exerted on the water. According to Newton's third law, the water will exert an equal opposite force back onto the hose. And then if you want to prevent the hose from moving backwards, you have to have a person here holding the hose. So the person will have to exert a force that is equal to the force acting on the hose. All right. So here they say, what is the minimum force required from a person holding the hose pipe to prevent it from moving backwards? So the force required by the person to prevent the hose from moving backwards is the same as the force acting on the hose, which is in turn the same as the force acting on the water. That's why we're doing the analysis on the water right now. Okay. Now, rate of change of momentum of the water produces the force on the water. So we want to find the force on the water right now. Force is rate of change of momentum. It is actually change in mass times velocity divided by delta t. When you're talking about change in momentum, it can either be something like this, mass times delta v or delta m times v. It depends on the situation. Change in momentum can be caused by mass times change in velocity. This one, I'm not sure whether you guys have noticed this before. You can have change in momentum if your mass is constant, but you have a change in velocity. You can also have change in momentum if your velocity is constant, but your mass is changing. Okay. So when you're talking about force being rate of change of momentum and you want to talk about change in momentum, it can be these two cases. Either mass constant but got change in velocity, or either velocity is constant but got change in mass. In your case, it's actually changing mass, but velocity constant. Your mass is changing by 90 kg per minute. Okay. All right. So here it will be delta m times v over delta t, delta m over delta t times v. Now delta m over delta t, this one is actually your rate of mass change, which is actually 90 kg per minute. All right, you already have this value here, but you want to change it to seconds. Okay, this one is per minute, you have to change it to seconds. So it's 90 divided by 60 seconds, then multiply with your velocity, you're going to get 13 Newton. So answer is A. Okay, yeah, there's a lot of things that you can probably try to think of from the question, but I think the most straightforward answer most of you will just do is you will just straight away do this. Okay, right? So 90 divided by 60 times 20 gives you 30 Newton. The rate of mass change is 90 kg per minute. the velocity with which your water is moving is 20. Just use these two values. Okay, so 8 is 8. The answer is 8. Okay, so that one is all right. Then I clear this one. Okay, number 9. A skydiver leaves a stationary balloon. Here the question says this. A skydiver leaves a stationary balloon and falls vertically through a long distance. Which graph best represents the variation with acceleration A of the skydiver with distance s traveled as she falls through the air? Okay. Now, this one, be careful a bit. This one is not talking about acceleration versus time. It's talking about acceleration versus distance. Okay. Yeah, and then one of the things that I mentioned to you before is that whenever you do your questions, and then they didn't mention air resistance is negligible, you have to always assume air resistance is in. You see, in your question here, when you read this, they never once mentioned air resistance is negligible, right? So you have to assume air resistance is present. Okay, so this one I better just make a note. So air resistance is assumed to be present since question did not mention it is negligible. Okay, so it did not mention air resistance is negligible. You have to assume it is present. Same like when you do your electricity questions, if they never mention that if they never mention internal resistance is negligible for your battery, you have to assume that internal resistance is present. Okay, I think I mentioned this before when I did some of the questions for you. Okay, so now we know that there's air resistance. If the skydiver falls, he will eventually reach terminal velocity. Okay, so from what you've learned so far for terminal velocity, we know that when someone falls, your velocity increases at a decreasing rate until you reach a maximum. Your VT graph looks like this. And then your AT graph, acceleration time graph, your acceleration will decrease until 0. It will decrease at a decreasing rate until 0. Your graph looks like this. Okay, so now these are your VT and AT graphs. The x-axis is with respect to time. But the one that you have here is talking about with respect to distance travel. So which one would actually be sensible for you? Actually, this one doesn't really need you to prove the graph shape. This one would actually be something that you can just use common sense. It basically what they're telling you is that this one is your skydiver, this one is your balloon, and this one is your skydiver. The distance measured is basically based on this. This one is how your distance s is measured. You can actually say that as the person falls, as your distance s increase, this one is s equals to 0. As your s increase, your distance increase, your acceleration by right should drop, right? This is the most important thing that you should know. It is also correct to say that your velocity would increase. Okay, they all follow this graph. Okay, but the gist is that you should recognize that the more you fall down from the start, the more your acceleration will drop. So you look at all these graph answer choices B, C, and D. This one is stating to you that as increase, acceleration increase. This one is saying to you as increase, acceleration is constant. This one is saying to you as increase, acceleration increase. But only this one tells you that as increase, acceleration decrease. So this is the correct one. The rest are actually wrong, just by using some common sense here. Okay, you don't need to go all the way to derive the shape. Okay. So answer for 9 is A. Okay, so that is all right. Okay, number 10. Number 10 is collision already. The diagram shows two spheres approaching each other head-on. Each sphere has speed u, one sphere has mass 2m, and the other has mass m. Which diagram shows the result of a perfectly elastic collision? So usually when it comes to perfectly elastic collision, one of the first thing we always look for is always the part where relative speed of approach is equals to relative speed of separation. Here I just made the short form. RSA is speed of approach, RSS is speed of separation. Now you just look at the first part here. For the case before collision, your two masses are moving in opposite directions. So the speeds must add up. Is u plus u giving you 2u. The next thing you need to do is to find out the relative speed of separation for the answer choices below. So you do the same thing like before last time. This one is answer choice A, moving in opposite directions. So you add up the speeds. Is u over 3 plus 5u over 3 giving you 2u. So this is actually the same as your relative speed of approach. Therefore, this is your elastic collision case now. Okay, but sometimes you need to be careful a bit. I mean, you have probably gone through a few questions where you have two different answers that have the same that tells you that relative speed of approach equals to relative speed of separation. In cases like that, you have to like do another separate criteria to determine which one is actually the answer. Because one of the things you would do normally is relative speed of approach equals to relative speed of separation. This one is number one you would do. If there are two possible answers, the next thing you probably would do is use conservation of momentum or use conservation of kinetic energy to determine. Okay, but the first thing you normally do is this one. It's only when you have two answers that are giving you this that you start to use a different criteria. Either you use conservation of momentum or conservation of kinetic energy. Okay, you probably have seen one or two questions like that, where two answers are giving you relative speed of approach equals to relative speed of separation. From there, you notice that you have to do some other criteria. Now, if let's say you did this for answer choice A, and then you notice that, yeah, you're already getting relative speed of approach equals to relative speed of, sorry, if you do this question and you do for A, and you got it the first time, that relative speed of separation is the same as relative speed of approach, my advice to you is to double check with the rest of the answers. See whether this is the only one, okay? Because if you're unlucky, maybe there's another one that also told you the same thing, okay? So you go and repeat the calculation for the rest of the answer choices just to double check. So this one is going opposite direction. Is you add up the speeds, u over 6 plus 2u over 3, you're going to get 5, 6 over u. So this is not the same, it's out. And this one below, they're moving in same direction. Take the higher speed minus the lower speed. So it's 2u over 3 minus u over 6, giving you u over 2. This is not the same. So this is out. This is not the same as your relative speed of approach. So this is out. Last one is just two of them sticking together, giving you u over 3. The relative speed of separation is just u over 3. Again, it's not the same as your speed of approach, so this is out. So now you double confirm already, this is confirmed to be the correct answer. Okay, so this is number 10. Okay, then number 11. You have a spherical object that falls through water at a constant speed. Three forces act on the object. Which diagram showing these forces to scale is correct? So they have actually drawn for you the forces to scale here, okay? This is very important to note, okay? So the consequence of something traveling in constant speed, by now you should know it means no net force, which in turn means the sum of upward force is the same as the sum of downward force. Okay, so in our case, we have an object that's falling through water. There are a few forces to consider here. That they told you there are three forces, but what are the three forces? The first one is your weight, which acts down. Because you're falling through water, you obviously would have upthrust. So you have upthrust as your second force, which acts up. And then the last thing would be drag force. This is your third force. It will oppose the motion of your sphere downwards. So these are your three forces. 1, 2, 3. So drag force opposes motion of your sphere downwards, so your drag force must be acting upwards. Okay, drag force always opposes motion. So if your object was moving down, drag force must be up. Okay. So back to the right side of my workings, sum of outward force must be equal to sum of downward force. My outward forces is drag force and upthrust. My downward force is weight. So R plus U must be equals to W. In other words, drag force plus upthrust must be equals to weight. So all you need to do now is to identify which of these arrows added up will give you the same. I mean, you see, there are two arrows pointing upwards, right? And then there's one arrow pointing downwards. You kind of have to use your ruler if possible, or yeah, it's better to use a ruler. You try to add them up, see whether the lengths are the same. If let's say for the top part, where I see that there are two arrows here, if I try to add this length over here, is the total length. Okay, this is getting really confusing. What you just need to do is this arrow you try to put over here. Then you see whether the total length is the same as this length. If this length is the same as this length, that means the forces are equal and opposite. Okay. So you look at the few answer choices. If you try to do them to scale accurately, you notice that this one is definitely out. These two added up will not be the same as the bottom. And then these two added up will be more than the bottom. It's only answer choice B. If you add these two up, it'll be the same as the bottom. Okay? Right? That's the significance of them telling you that the forces are drawn to scale. You actually kind of have to see the scale properly. I mean, you have to see the length properly. Okay, answer choice B is the answer. Okay, then after that, we go to number 12. Number 12 should probably be one of the last questions we do. Okay, now two forces act as a couple. What statement about two forces must not be correct? In the first place, what is a couple? A couple is a pair of equal but opposite force that is separated by distance. They should not be acting along the same line of action. Okay, so what is not correct for a couple is that they act along the same straight line. This is definitely out. If let's say I tell you that this one is force F, and then this one is force F, and there's a separation between them, this one is coupled. But if I have the same force F, and I have a force F like this, and they act along the same line, there's no distance, this one is not a couple. So this one is wrong. Okay. They act in opposite directions is correct. They are same type of force. That one should also be correct. Must be same type of force. They have the same magnitude. Okay. So A is definitely the one that is out. Right. Okay, so that one is okay. Right. Then maybe I just do one more question for you guys then before I end this. Now you have a sign outside a shop that is suspended from a rusty horizontal hinge at the top end. The sign hangs in equilibrium at an angle of 25 degrees to the vertical as shown. The sign is a square of side length 52 centimeter and uniform thickness. It has a mass of 36 kg. What is the moment caused by the weight of the sign about the hinge? So this one, they just want moment caused by the weight about the hinge. So this one is your pivot. So what is the moment caused by your weight of the sign itself? The weight will be acting right over here in the middle. Okay. So if I know that the sign has length of 52 centimeter, which is this one, the weight will be acting right in the center. Okay, so what I could do is that I could resolve the sign horizontally, the length. This one will be 52 sine 25. Half of that distance will be half 52 sine 25. Okay, so my moment caused by this weight is force times perpendicular distance. My force is my weight, which would be 36 times 9.81 because the mass is 36. But my perpendicular distance would be half 52 sine 25. Okay, my perpendicular distance is going to be this one. If this one is my force, the line of action of my force, and I try to draw a line parallel to it, passing through the pivot, you can clearly see that this one is my perpendicular distance. It's going to be half 52 sine 25. One thing to be careful of is to change your length to centimeter to meter. This one is centimeter, right? Remember to change it to meter. That's why it's 0.52 here. So your final answer would be 38.8 Newton meter round to 2 SF is 8. Okay, so that's that.